Today, let's talk about one of the greatest achievements in human history. It's a theory that is so good, it's practically perfect, and yet at the same time, it's so incomplete that you could call it a beautiful failure. We're diving into the standard model of particle physics.
It all really boils down to the most fundamental question you can ask. What is everything really made of? I mean, if you could just zoom in on your hand or your desk or anything and keep zooming way past the molecules, past the atoms, what would you find at the very bottom of it all? That's the question that's been keeping physicists up at night for decades.
Now, to really get why the Standard Model was such a game changer, we have to rewind a little bit. We need to go back to a time of total, absolute chaos in the mid-20th century. A time when our picture of the universe was, well, kind of falling apart. Welcome to what they called the particle zoo.
And look, I am not exaggerating when I say it was a mess. The more powerful our particle accelerators got, the more confusing the world looked. Instead of finding a few neat, simple building blocks, scientists were just getting swamped with a flood of brand new, totally unexpected particles.
I mean, just try to put yourself in their shoes for a second. You're discovering dozens of new fundamental particles, and none of them fit into any theory you have. There's no rhyme or reason to it, no periodic table to get them organized. The forces that hold atoms together, a total mystery. You're seeing particles decay in ways that just make no sense whatsoever. Physics was screaming out for some kind of unified theory to tame this whole zoo.
And then, out of all that chaos, an idea started to form. An idea of just breathtaking elegance. As physicists sifted through all this data, they started to realize, hey, maybe you don't need a whole zoo. Maybe you just need a handful of truly fundamental particles, arranged in a beautiful, simple, structured way. This was the birth of the Standard Model.
All right, so here is the heart of it. The Standard Model says that everything, all the stuff you can touch and see, is made from just these 12 particles of matter. They're called fermions. You can think of them as the ultimate Lego bricks. They're neatly organized into 3 generations, where each one is just a heavier, more unstable copy of the one before it. But here's the real kicker. All the stable matter in the entire universe, that means protons, neutrons, electrons, is made from just that first generation. The up quark, the down quark, and the electron. That's it. That's you, that's me, that's everything we know.
Okay, but obviously those Lego bricks don't just sit there, right? They interact, they stick together, they push apart, they do stuff, and that is where the second group of particles comes into play, the bosons. If the fermions are the bricks, then the bosons are the forces. They're like the universe's messengers, carrying the instruction manual that tells all the bricks how they're supposed to behave.
So let's meet the team. First, you've got the photon. You know that one. It's light, it's electromagnetism. Then you have the gluons, which are incredibly powerful. They literally glue quarks together inside protons and neutrons. Then there's the W and Z bosons, which are in charge of things like radioactive decay. And finally, you have the celebrity of the group, the Higgs boson. Its job is totally unique. It doesn't carry a force, but it's what gives all the other particles their mass. Without the Higgs, everything would just be zipping around massless at the speed of light.
So there you have it. That's the theory. 12 matter particles, 4 force carriers, and the Higgs. It's a really neat picture for sure. But here's the thing about physics. A theory is only as good as its predictions. And this is where the Standard Model went from being a clever idea to one of the greatest triumphs in the history of science. Just look at this track record. The model didn't just explain the stuff we already knew about. No, it actually predicted the existence of particles that nobody had ever seen. The math said things like the charm and bottom quarks had to exist, and boom, 1973 we found them. It predicted the exact properties of the W and Z bosons, and sure enough, 1983, there they were. For decades, it just kept making these incredibly bold predictions. The top quark, the Higgs boson, and one by one, scientists hunted them down and found them, exactly as the theory said they would be.
And we're not talking about ballpark predictions. Things like the magnetic moment of the electron have been tested and confirmed to an absolutely mind-boggling number of decimal places. So this isn't just a nice story. It is arguably the most rigorously tested and precisely confirmed theory human beings have ever come up with. So that should be it, right? End of story. We figured out the universe. Case closed. Well, not quite. Because for all of its incredible success, there are huge, gaping holes in the Standard Model. It's like we found the code for the universe, but entire chapters are just missing.
So based on everything we can see from cosmology, all our best observations, this is what our universe is actually made of. And here's the part that's going to blow your mind. See that tiny little 5% sliver at the top? Normal matter? That's it. That's everything the Standard Model has ever described. Everything we've seen or touched or made in a lab. Just 5% of the cosmos. Let that really sink in for a second. Our best theory of reality, our most precise, most tested, most successful theory has absolutely zero to say about 95% of what's out there. It can't tell us what dark matter is, that invisible stuff that holds entire galaxies together, and it has no clue what dark energy is, the mysterious force that's making the universe expand faster and faster.
And the list of problems just keeps going. The Standard Model famously just ignores gravity completely. It also can't explain why these little particles called neutrinos actually have mass, which is something we discovered that directly contradicts the original theory. It doesn't explain the huge question of why we have a universe made of matter at all, instead of one that was annihilated by an equal amount of antimatter. And maybe the most annoying part for physicists, its beautiful equations depend on about 19 different numbers that we just have to measure and plug in by hand. The model gives us no reason for why they have the values they do.
So, where does that leave us? Well, we have this theory that is, at the same time, this monumental achievement and deeply incomplete. But you know what? That's not a failure. In science, a mystery is just an opportunity. These cracks in the Standard Model aren't the end of the road. They're the signposts that are pointing us toward a new, deeper kind of physics.
Really, the way scientists think about it now is that the Standard Model isn't wrong. It's just a fantastic approximation that works perfectly in the world that we live in and the experiments we can run. It's a huge, essential chapter in the story of physics, but it's not the whole book. It's a monumental step forward for sure, but it was never going to be the final answer.
And that, of course, brings us to the big, exciting question. There are ideas out there, of course, things like supersymmetry or string theory that are trying to fill in these gaps, but so far we have no real evidence. The hunt is on for whatever comes next, for a theory that can finally make sense of that other 95% of our reality. So what do you think is out there? What comes next? What will be the theory that finally replaces the most successful failure in the history of physics?